Hey folks, in this video we're going to start putting some things together. So up until this point we basically had a pretty long discussion on how do we map a key to a hash, right? And what should a hash look like, what behavior should it have, what makes it a good hash. So we spent some time on that. All right, so far things are looking pretty good. We have a way basically to get a key to a number, and that number, right, hopefully I can use it as an index into an array, right? So if I want to store my key value pair, right, I can maybe do it. Now, things are getting a little bit trickier, right? So the simplest approach I could possibly have is basically to say, oh, hey, I'll just use that hash directly, right, as an index. I'm going to store in, my stuff. We already know, though, that's not really going to work because, hey, that hash value, right, could be anything, right? It could be something much larger than m. And so we had that kind of last process there where it's like, well, we should do a modulus, right? So we'll plan basically, right, that our basic thing here, right, is basically do a modulus, right, to whatever we're adding into our table. Okay, so that would be, it's a reasonable thing to do, right? We don't really have a choice because that m table, or that m size array, right, is going to be for sure smaller than the values I see as hashes. So we'll do this, right? This is our initial thought: is make that modulus operation fit the value into the array. So that's fine, and let's actually look at the example on the right hand side. Let's see what happens, I guess, if we were to do that. So let's take a look at the right hand side. So let's say we have a bunch of integers and we just want to hash them. What happens? So obviously, right, hashing an integer is pretty simple because an integer, right, I could just say it is itself, right? We're not doing any work; it just automatically is a hash. And then, right, via our previous discussion, what we said is, hey, we're going to modulus it by m. So here, what we're doing is we're saying, hey, there's maybe some sort of array that's of size 3. And so our whole kind of computation here is basically say, hey, my integer mod 3, right? What is the value of it, right? Hopefully, that's something I can use as an index into an array. So let's try looking at that. So if I have my index or have my integer 0, right, and I put it through this hashing operation, which again, it's not really any work to hash an integer, right? We just have to really do the modulus to get to fit in. Well, I get 0 back out. So this is kind of like the index in the array where it wants to go, right? So if I have number 0, it wants to go into the index 0. Fine. Do this again. 1 wants to go into index 1. 2 wants to go into index 2. Again, right, all I'm really doing here is doing a modulus operation. But then here, once I get to 3, 3 mod 3 is 0. So these are giving me the same number. And this goes on. If I go to 4 and 5, those generate 1 and 2 respectively, and those end up colliding with other things, right? So there's a collision over here and a collision over here. This is not good, okay? All of a sudden, right, things are hitting one another. There's nothing I really can do, right? So no matter what, right, because my domain because my range, right, of hashes is so large, and it's very large, right? So it's very large, right, relative to m, right, the size of the array. I will always have some sort of point, right, where basically, once I've done all my operations, I'm going to have collisions, right? I'm going to have things that run into one another. So this is a problem, and we can't really avoid it, right? Unless we make m really large, which means a lot of space, we'll have to deal with things that want to be placed at the same place in the array. So what do? We need to have some sort of a collision resolution mechanism, which is going to be the central topic of this module. So we have two overall mechanisms. The first is called chaining, or sometimes they're more specific and they say it's separate chaining. The idea is this. You have an array, and in your array, if you have different elements or different keys, right, that hash to wanting to go to the same index in that array, put them there, right? Make every index in your array a pool, right? And or a bucket, and you're just throwing things in there, throwing things in there, right? And you do that every single, stop in your array. Every single index in your array, you have a bucket. Really, it's a linked list. That's why they call it chaining. Chain, linked list, right? Kind of visually the same. So that point there is we don't really avoid collisions, right? The way we resolve them is saying, okay, I'm going to allow things to end up at the same index. I'm just going to have a bucket there where I can put them all into that bucket, and that bucket just has to deal with it, right? It has to contain them all. So that's the first approach. The second approach is something called linear probing. So linear probing is a little bit different. Linear probing says, okay, you know what? You're going to have the array, but in that array, you're only going to keep one element per slot, which is kind of intuitive. And so, if you have something, you hash it, and you want to put it in an index, you basically say, okay, I'm going to do that. Look at the index. If it's empty, put it there. Okay, fine. If it's not there, go and look for another space that's available. Okay, and there's kind of different ways to do that. To say, okay, go look for a different space. So this is, this is a slightly different approach. So it's linear probing. As a quick example here, right? So let's say we have something that's like, we'll do two examples here. Let's say we have our m equal 3 for 3 spaces. And let's say we basically have, we insert, so let's say we insert the numbers 0 and then 1, 1. Where would they go in these different conceptual mechanisms? And obviously, we're going to spend a lot more time on these. We're going to go through their implementations. But for example, like the chaining one, and this is meant to be an array here. This is index 0, 1, 2. For chaining, basically it says, okay, you know what? You're going to put, 0 over here. Right, there's a little linked list there, right? It's a bucket I'm throwing things into. And then for this one, right, it's like I'm going to put 1 there and then another 1 there. So it's like, well, that index in the array knows about a couple other places. Versus for linear probing, the way linear probing would look is you have your 0 here because that's where it wanted to go. You have your 1 here because that's where it wanted to go. And you probably put 1 again. 1, though the space it wants to go is already occupied, so it goes and finds the next available space, which is going to be 2. So it actually ends up over here. So yeah, basically it's like, do we allow everything basically to cluster up when it does have basically a collision, or do we basically force it to spread out? So these are the two different approaches. And ultimately, right, linear probing is what's going to get us our constant time. Chaining will look a little bit, it'll occasionally look like linear time, which is not so good. All right, so these are 2 ways to address collision resolution in terms of hashing. So in the following videos, we're basically going to go into depth on how we actually implement a chaining-based hash table as well as a linear probing-based hash table.